Okay, so this is just a short section, 6.5 on arc length. So I'll kind of go through where the formula comes from so you have a little understanding, and that can help you memorize it. And then I'll go through one of the bit more complicated problems. When I say complicated, I mean complicated algebraically. So when we talk about arc length, okay, what we mean is, suppose we have a function, whatever the function may be. We'll just call it f of x. And we have point A, interval A to B, and we want the length from A to B. Now, so just like everything else we've been doing in the past videos, is we're using this idea again of Riemann sums, right? And using this idea of summing a whole bunch of pieces, n number of pieces, as n goes to infinity, and essentially we're going to take an integral. But when we're talking about arc length, it's going to change a little bit in what those pieces are. So suppose we had, okay, we break it up into our sections, you know, and obviously you got to imagine these being very small, but we don't care necessarily about the area underneath. What we care about is the distance from one to the other, right? So from here to here. And if we sum all these infinitesimal, all these little tiny, infinitely amount of distances, we'll get the complete arc length from A to B. Well, let's think about that. You all recall a distance formula, perhaps, of a line where you took, remember this? X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Essentially, anytime you subtract x's, that's a change in x squared plus a change in y squared. So that's what we're going to utilize as we go through this distance formula. And this comes from our, you know, if I blow up this rectangle, right? Okay, there's my change in y and my change in x, right? And the square root of change in x squared plus change in y squared is going to get you the distance from here to here. And that kind of makes sense. So if you think about it, we can do a little manipulation with that particular formula. So when we talk about our arc length, if we start with thinking about it as change in x squared plus change in y squared. Now I'm gonna do this very generalized. If you look at the book and go through the sections in the book or in the notes, you're going to see all the subscripts. I'm taking the subscripts out of it for now and just kind of giving you a general idea of what's happening. So, yeah, we're going to do a bunch of algebraic manipulation. You're like, why? But it works. So let's suppose I want to factor out change in x squared. Well, you can do that. You get a 1 there. But to do that, you actually end up with change in y squared over a change in x squared. And if I multiply it back, you'll see you get exactly what we have. Well, that is going to then equal 1 plus change in y over change in x squared. And then I have this delta x squared, but I'm going to move that outside as just a delta x and take away the square because it's now outside the radical. So, what is delta y over delta x squared? What exactly is this piece right here? Well, come on over to this blown up triangle, which really is an arc we're looking for, right? So if you recall something called the mean value theorem. You learned it in Calc 1 very briefly. And the mean value theorem basically states that between any 2 points, right, because this, the slope of this line is obviously change in y over change in x, the slope, not the distance. There exists a point, right, somewhere that has the exact same slope. So there exists a point, and we called it, if you recall, f prime of x, that was equal to delta y over delta x. So in other words, there exists a point between these two where the slope or the derivative of the function is equal to change in y over change in x. So all that does is now allows us to come down here and say, okay, this is now equal to 1 plus f of x prime, f prime of x squared dx. And again, that is just one triangle. We're going to sum n triangles, and then we're going to take the limit as n goes to infinity. We've seen numerous times by now, taking the limit as n goes to infinity of n summations is simply an integral from a to b of 1 plus f prime of x squared delta x. Now, as we saw in past videos, we found that at times it's actually easier to describe a function in terms of y as opposed to in terms of x. So you can also do this with your function solved for x equals, which would be, we won't use f, we'll use g in this case, of y squared delta y. So again, some functions, they're easier to write as x equals, other functions are easier to write as y equals. So you can use either one and differentiate with respect to x or with respect to y. But for the most part, if you just get the general idea. So basically, it is derived from your basic distance formula, because what we're going to do is take minute, little tiny distances across this curve and add them up as we approach infinitely many distances to the point where we get an exact value of the distance from A to B. So again, we're going to do one problem. It's going to be a little bit more robust algebraically, but it's a good example to kind of take a look at. So these are pretty straightforward. This one is going to be number 14. Again, I always try in the videos to do these even problems because you don't have them worked out. And this way you can practice some of the odd ones in our textbook. And basically our directions here are just to find the arc length of the following curves on the given interval. So for 14, we have y equals x to the 3/2 over 3 minus x to the 1/2 on the interval 4 to 16. Now, you can always graph it in Desmos if you want to take a look at what it looks like, but it's pretty straightforward. Since our function is solved for y and our function has x's in it, we are going to simply differentiate with respect to x. Now, as you can see, so we are going to use from 4 to 16, 1 plus, we will need y prime delta x, or if we want to call y f of x, it's f of x prime. Well, we got to get that. So let's figure out y prime, or f of x prime. All right, go over to your function. So let's now be careful. You're not doing an integral right now. You're differentiating. You're finding a derivative in this case. So x to the 3/2, we're going to drop it down. We're going to multiply by 3 halves, make it x to the 1/2, divide by 3. We'll clean that up in a second. Again, drop it down. It's negative 1/2. Move the 1/2 out front and drop it down. All right, clean up your derivative. We get x to the 1/2 over 2, because my 3's cancel, minus 1 over 2, x to the 1/2. For a second, I'm going to go ahead and put it in radical form. So square root of x over 2 minus 1 over 2 radical x. Because, as you can see, it's not enough to find the derivative. You have to square the derivative. And we can square that derivative. So y prime squared. Square the first term. We're just squaring a binomial, which means you square out the first term, which is going to give me x over 4. Multiply them together. Well, what happens when you multiply? Well, they cancel, and you have negative 1/4, but then you double it. So squaring a binomial, and plus 1 over 4x. So that ends up being x to the 4th minus 1/2. So let's talk about this for a second. That means this is what we call a perfect square binomial. Meaning, if you take the square root of it, you get back to that. But don't I have to add 1? What happens when I add 1 to this function? So my y prime squared plus 1. Well, I'm going to add the 1 to the 1/2. Doesn't that give me positive 1/2? This is where you have to get creative, I guess, or really think about it. The only difference between the function I have in red and my new function is the middle term. One of them's negative and one's positive. But isn't the function I have boxed in red a perfect square binomial? So then this one is also a perfect square binomial. The only difference is, instead of the minus sign that yielded a negative 1/2, I want a positive 1/2, so I'm going to make it plus. Squared. So now, honestly, that is just kind of following what you've done, making notes, understanding your algebra and your factoring, your perfect square binomials, noticing the difference between them. When I come and put it back, I'm going to change I have this 1 plus y prime squared is equal to square root of x over 2 plus 1 over 2 radical x to the 1 squared. Sorry, I don't know why I wrote 1/2. But the square cancels. I'm going to change that square root of x to 1/2 over 2 plus 1/2 x to the negative 1/2 dx. Because the square just cancels the radical. Yeah, I kind of have something I can easily differentiate now. X to the 1/2 over 2, raise it up. It's x to the 3/2 times 2/3. When you multiply 2/3, you got a 2 on the bottom. The 2's cancel. You're left with 3. All right, 1/2 x to the negative 1/2. You're going to raise it up. You become positive 1/2. You're going to divide by a half, which is multiplied by 2. It cancels the 1/2, and you're left with x to the 1/2. And this all goes from 4 to 16. You can kind of throw the math in there. You have 16 to the 3/2 over 3 plus 16 to the 1/2 minus 4 to the 3/2 over 3 plus 4 to the 1/2. Square root of 16 is 4. 4 cubed is 64/3 plus 4. Square root of 4 is 2. 2 cubed is 8 minus 8/3 minus 2. So I have 64/3 minus 8/3 is going to give me 56/3 plus 2, which is 56/3 plus 6, not 6, sorry. Yeah, 6 over 3. And that is our answer, 62/3. So again, this one is pretty short. I'm just going to go through one example with you, practice with the ones in Math Lab, and see if hopefully understanding where the arc length formula comes from will help you actually memorize what it is.